Hello and welcome to watch this video about thermal buildup or heat accumulation in pumping systems. Heat accumulation is an important but often overlooked phenomenon. It happens during flow recirculation conditions. The continuous and significant recirculation can lead to temperature rise, which can result in separation inefficiency, pump seal degradation, and potential system failure if the heat accumulation is significant and it is not removed. Let's start with an example that is made in Aspen Hysys dynamic environment to investigate the process of heat accumulation. In this PFD, you can see a separator and it receives flow from upstream processes. And we have a pump that removes the liquid from the separator. And we have the level control, which manipulates level control, the control valve to maintain the liquid level in the separator within the set point. And also we have pressure control just in place. We don't go the way we do the pressure control. Here we assume that the pressure control is done by the control valve, and we are not focusing on that. In addition, the mean flow control also is in place because the pump of which we are in discussion is a centrifugal pump. As you can see here, the pump will add about 1 degree centigrade in each pumping cycle. So if the liquid goes forward to the downstream processes or export, then that temperature increase will not affect the loop. But if the mean flow recirculation is initiated or is already in operation, or already is a case, in this situation we have a portion or in some condition a full part of the flow with the increased temperature will return to the separator, and that cycle will continue, which can lead to the temperature rise in the vessel. For systems where we have coolers in place in the loop, and you are in the loop, then we don't have that concern with the heat accumulation, so we are not discussing those systems. But for the system that they don't need cooler in normal operation for any reason, this can be a risk. So when the situation will be risky and it will be a potential for heat accumulation, the situation could be reduced production when we have less flow to the system. And the pump is sized for higher flow, therefore the pump goes to mean flow, and part of the heated liquid will return to the separator, and that can continue as normal operation. And in this situation, for reduced flow situation, the increase in temperature is not infinite. So it's a finite change in the temperature, and it's wise to find it out for any reduction in the production to see what is the maximum steady state temperature when the pump is going through mean flow recirculation, partial recirculation. But the extreme cases, for any reason, if we have no inflow to the system, in that situation, the full flow through the pump will be recirculated, so the only mean flow will be flowing in the system, and that can rapidly increase the temperature depending on the size of the vessel and the heat transfer, etc. in the systems, and also the inefficiency of the pump. All these factors will affect the time to reach to a certain temperature, which can be acceptable or it can be not acceptable due to the design requirement for the seal and bearing of the pump, etc. Let's start the investigation. I will run the simulation. And first, I do the reduce production. So I artificially manipulate the control valve just to show the reduced flow to the system. So as you can see, the flow here in the chart is the total flow through the pump, which is set to the mean flow requirement. As you can see here from the pump curve, the pump is on the mean flow and is 500 cubic meter per hour. In that situation, you can see here you can some transitional behavior for the system, and it can be seen that the level was below the set point. So for a while the valve was closed. Now it's going to open, and it goes through the transition to stabilize. And it seems the liquid inflow is around 50 cubic meter per hour. So it means 450 cubic meter per hour is recirculation around 90%. So the temperature initially was 49 degrees centigrade in the separator liquid phase. And now we approached around 56 degree, and it's also increasing still, but not very steep. So we are approaching actually a steady state condition within some period of time. As you can see here, that temperature rise of around 7-8 degrees centigrade happened in around 0.4 hours. So it's about 20 to 25 minutes. This situation, which can be a typical turn down for the processes when you have a reduced production. So if the final steady state temperature is acceptable and within the design requirement regarding the temperature, then we can live with the pump and live with this temperature rise, but still it will be very inefficient in terms of energy, because 90% of the flow is recirculated, and that's a waste of energy, and logically should be avoided. So the best move in this situation is to revamp the pump to make the rating point to a much lower flow and eliminate or reduce the mean flow recirculation. This is typical and classic way of coping with that situation. Additionally, it's wise to have a temperature high alarm or temperature safety alarm or trip level in the discharge of the pump to protect the system in such scenarios if the situation goes to extreme and the temperature approaches the design temperature of the system, especially the pump. So now you can see the temperature still not stabilized, but it's like around 59 degrees centigrade. It's about 10 degrees higher than the previous normal operating temperature. But if the flow is completely stopped, what can happen? So this is an extreme case for this study. So just remember, every loop has its own characteristics. So it's wise to simulate dynamically to find out the temperature profile during the transitions, and to see what is the risk and how long it takes to approach the design temperature, and be aware of the reduction in the flow. When the flow is completely stopped to the system, then the temperature rise will be almost infinite. So it can reach definitely the design temperature of the system. It's only time dependent on the size of the vessel itself, and also the total liquid in inventory and the heat transfer with the environment. It might be very quick, and it might take a few hours to reach that situation. So in general, it is wise to solve the issue uh, by routing them if there is an opportunity to route the main flow line to upstream a cooler. If that is in place, then it can help the situation to improve it and to mitigate the risk. Uh, but as a primary protection, it is wise to have, as mentioned before, a high temperature alarm and high temperature trip level to protect the system against this situation.